Okay, so good morning, everyone. Thank you for joining this webinar session for the Netpore First Action project. And today we have two talks, and it is my pleasure to introduce the first speaker of today's session, who is Abel Santos from the Adelaide School of Chemical Engineering. And Abel has received his PhD in 2011 from the University of Tarragona in Spain, and is currently an associate professor in Adelaide University. And he has an impressive track record of more than 100 research papers and more than 6 million in competitive research grants. And he is internationally recognized as one of the top 2% scientists in the world by Stanford University, and is being awarded several recognition by the Journal of Materials Chemistry C and ACS Applied Materials and Interfaces as emerging investigator in this field. And his research focuses on the electrochemical engineering of nanoporous anodic alumina structures and their integration for several applications concerning photonic and optoelectronics technologies, such as sensors, lasers, photonic crystals, and so on and so forth. So it is really my pleasure to introduce Abel today, who will give a talk about tailored engineered nanoporous anodic alumina, and is going to give an overview from down under. So please, Abel, you can share your screen.
Yeah, thank you. I will try to share my screen. This is the second one. Yep. Okay, let's see if it works. Can you see the screen?
We can see your screen.
Yeah, you can see the presentation? No, sorry. Let's see if I can. Oh, sorry, I will stop. Yeah, I will stop sharing. We'll do the screen slides. Yep. Oh. This is the one, screen share. Yeah, this one, share. Why is doing this? Yeah, sorry, I will share it now. Was showing. Yeah, can you see now the presentation?
We can see your presentation
in
full screen. Thank you.
Yeah, sorry. Thank you very much for the nice introduction. Looks a lot of gold coding, but it's not that cool as it sounds. So I'm just a normal researcher. So today I decided to do a more general presentation or overview of what we do here in our lab in the University of Adelaide. So you have a clear idea of what we do basically with porous alumina and the different applications that we work. So I think it's more fun than talking about one specific work. So, well, you already introduced me. I am originally from Spain, but I moved here in Australia in 2012. Well, at the very beginning, 2012. And it has been already more than 11 years now here in Adelaide. And currently I'm associate professor at the School of Chemical Engineering. So if you have the opportunity to look at, sorry, will you the laser pointer? So if you have the opportunity to come to Australia and have a look at the map, so we are here at the very south. That's why the state is called South Australia. So Tushar is here in Sydney on the side in the east the state. And yeah, it's a very nice place and very, very big, as you can imagine. So yeah, very, very nice. And here, well, I will introduce with more detail our research interest and what we work on later. But currently, this is my lab, my team. So we are two early career researchers, Siuyi and Cheryl. And then we are currently eight PhDs. Here in the image, there are only 6, but there are 2 new PhD students joining us. Then also 2 masters and 4 undergrads which come and leave because they are just with us working on the projects. And then we have different funding agencies. We have been lucky enough to survive in this very tough enterprise that is research. And we have a small, but I think it's very nice lab as well with a dark room for lasers and different optical tables and so. So it's pretty. I think someone should be mute, right? Yeah, all good. So
no,
I will
tranquila.
start.
Mira, ¿sales ahí? ¿Ven al café?
Sorry, can people mute the?
Yeah, I'm
no, yo no me estoy conectada, es un webinar, no. La cámara y el micro. El micro no lo sé.
You can mute it. Sorry. Yep. All right. So no worries.
No,
so
I'm not able to mute
That's okay. No worries. I think
Okay,
it's okay.
sorry.
Yeah, no, it's fine. No worries.
Thank you.
No problems. Oh, good. Well, basically what we do is we produce alumina. We do this process by electrochemical oxidation. I'm not going to enter into details about the process because Jan Maka gave a very nice introduction to this electrochemical fabrication process, which is called anodization. So alumina is pretty much the same than titanium nanotubes. Slightly different in terms of the properties of the material, but the fabrication process is very similar. So what's the difference with titanium nanotubes? Well, it's much easier to get very nice, well-defined structures like this one in the schematic with hexagonal self-organized structures within different geometric parameters, usually in the nanometric range. And that's a very good advantage because you don't need to use expensive nanofabrication technologies, not even a clean room. You can pretty much fabricate it in a garage. The acid electrolytes are not so dangerous as HF that you use to produce silicon. So that's very good advantage. And as you can see in this image here, this SEM image is in the cross section and the top view. So it looks like a honeycomb. It's not perfect because of the grain boundaries of the aluminum, but it can be fabricated perfectly organized with a nano patterning process. And the pores, typically they are cylindrical from top to bottom across the thickness of the material. So what we do basically is to play around with this material. I started to work on this material during my PhD, and I have a stick to it. Is this the right approach or not? I don't know, but one of my premises or my motto for doing research is the first thing is to have fun. And I have a lot of fun working with this material, to be honest. What is our vision to work with this material? Well, in principle, is to engineer nanoporous anodic alumina-based structures, and then we harness the properties of this material at the nanoscale for different applications and try to address fundamental questions in these applications. So the center of our research is NAA, and then probably the most direct application of it is the fabrication itself. So there is a lot of fundamentals of anodization technology that we like to work on and keep working on throughout. Then also sensing has been a big component, especially when I had the pleasure to work with Tushar back doing his PhD. We did a lot in the sensing space for chemical and biosensing. Then photonics in general as well. This is something as well that we started together with Tushar, and then after, so I decided to push forward when I became an independent investigator. So we create basically photonic crystals. We do also a bit of plasmonics, and now I start doing some hybrid systems between plasmonic and photonic crystal structures, and then photoluminescence and lasing. I will show some examples later. Then we are also start working now in green energy generation, specifically in water splitting via photocatalysis and photoelectrocatalysis. And then also environmental remediation. We have done a lot of work in basically the relation of organics by photocatalysis. And now we start also working on photoelectrocatalysis with semiconductors. And then finally, more recently, we start working on iontronics. Well, iontronics, I will give you another introduction to it later. But basically, it's about controlling the flow of ions along these nanopores and then generating ionic current rectification, which can be used for different applications as well, like sensing or energy generation, osmotic energy generation. So how everything started? So in my case, well, it started in the group NEFOS, which is in the University Rovira i Virgili. So they are in that group. When I started my PhD, it was focused on development of photonic crystals. And somehow it's like when a kid grows around toys or football, right? So you get this, and I got that from my PhD. Then also a very important inspiration from the beginning of my career was the works by Uli and Masuda. So, they were like titans in the field. So I got inspired by them, and I tried to copy. Excuse me, it's very annoying that people keep the microphone open,
Unfortunately, I'm not able to mute the other people.
It's really hard to present it like that. Sorry.
Yeah.
I'm sending a message to those people right now.
Yeah, thank you.
Sorry, Abel, for that.
No, good. Yeah. Anyway, sorry about that. So basically, I got inspired by these two people, right? So it was highly inspired, and I don't aspire to be like them, but you know, you can see some fingerprints in my own work from their original studies. Then also a very strong source of inspiration for me was to look for analogies between porous silicon, which was much more developed technology, especially photonic crystals in porous silicon, than in porous alumina. So I got tons of inspiration from the works of Sylor, Canham, Volker as well. So it was like, right, so master your material and try to apply the concepts that have been done in porous silicon. So that was a very successful venue, perhaps, at some stage in my career. And for me, the turning point was the year 2016, where I published this was the last year in which I published as researcher, right? A person that goes to the lab and does the experiments. So this year was very successful. I published 4 nanoscales. And each of them, I think, are very good advances in the field of porous alumina mostly, right? So, for instance, you know, like there was the first initial pulse ionization to mirror rate filters, then also bandpass filters, optical encoding. This was just mimicking what Mike did in porous silicon, and finally also the introduction of apodization signals in porous alumina, which was not done before. So they are not super top studies, but you know, in the field, I feel happy to have been able to contribute with this. Then the beginning of my career as chief investigator, well, I started. Well, when you...
Możemy chyba tylko zapytaj tam na dole, czy tam wiesz.
Excuse me, please. Could people turn off the microphones? It's really annoying. I'm sorry that it sounds very bad, but you know, like my head is crazy now.
Of course, Abel. Unfortunately, I'm not able to.
Yeah. Anyways, let's see if I can continue. It's like it's just very annoying. Anyway, so when I started my career as chief investigator, so then I decided, right, so what is the path to follow? So I saw some venue in developing nanoporous anodic alumina photonic crystals. And one of the main focus that I had is, right, so how we can overcome the intrinsic limitations of this material to do very nice photonic crystals, right? So I read some work by Li Xuan, his team, and he used in one of his studies highly concentrated sulfuric acid. He used high temperature. I used low temperature to avoid the etching of the alumina during the fabrication, and also the mild anodization condition. So that gave a lot of controllability in modulating the porosity of the material. Then what I was saying, so another advantage was that with these conditions, you can overcome the current density voltage recovery, because, you know, when you change the input current or voltage, the output voltage or current changes very quickly. So that's an advantage to induce modulations of porosity by the input current density. Then also that's the consequence of that, and also to avoid excessive etching as well at low temperature. And also another advantage of these conditions is that you generate very tiny pores. So in these tiny pores are practically the scattering because of these pores is very small, because they are in the range of 5 to 10 nanometers. And also you can generate a relatively high porosity contrast between the layers of high and low voltage or current, and increase the refractive index. So then after this, you know, like the next step was, right, so let's generate different types of anodization profiles. And we tried quite a lot of them, like sinusoidal, sawtooth, square, multisinusoidal, Gaussian-like as well, with Professor Marshall as well. So we did a lot of things in this space. And of course, with anodization profiles come different types of photonic crystal structures that we have explored throughout the time. So now I want to introduce what is a photonic crystal, right? So for those of you who do not know. So, well, I will take the analogy of an atomic crystal, right? So everyone more or less have an idea of what the sodium chloride structure is and what when you shine X-rays, right? So you get a diffraction pattern. So in this diffraction pattern, which is the position of these, these very sharp peaks, right, are interrelated with the structural features of the atomic crystal. So a photonic crystal is something similar, but instead of atoms, you do modulations of what we call refractive index or effective refractive index or dielectric constant in the space in 1 dimension, 2 dimensions, or 3 dimensions. And they are much bigger separation in terms of as compared to the atoms, right? The atoms are in the Armstrong size. The photonic crystals usually are in the visible, right? So the features are more in the nanometric scale. And when you shine light, in this case, visible light, so then you get these reflections, these peaks, which are not the same, but are quite similar, to resemble these diffractions of the XRD. So, but in the UV visible. So with that, we can modulate the way in which this material interacts with light. So in our case, what's the analogy? Well, we're using a porous material. So in this case, here is a solid 1-dimensional photonic crystal in which you have periodic variations of refractive index in depth. You have high or low, and you are, the spacing and the refractive index, you can engineer that. But how we do it in a photonic crystal? Well, there is a similarity when you modulate the pores. And this is a very ideal example of what I'm trying to use, which I take the opportunity to use this idealized model to explain how the effective medium approximation works, right? And how this structure is actually the same than this, right? So you have a pore, right, in which you modulate the porosity in depth as you go through the ionization process, and then you decompose this pore into the 2 components in terms of refractive index. So then you have at the center of the pore, you have air, the refractive index of which is 1, and then outside is alumina, which is 1.7. Let's assume that it's around that value. So what does the effective medium approximation? Well, so the effective medium approximation, what it does, it calculates an average of refractive index based on the fractions of air and aluminum oxide, and calculates an average at each section of the pore. So then, as you can see, we are creating this modulation of effective refractive index. It's effective because it's a porous material, of course, and there are two components, right, embedded into each. And with this approach, by anodization, we can create different types of photonic crystal structures because we can engineer the effective medium. There are different models of effective medium. I'm not going to enter to comment about them, but yeah, that's the basic principle of generating these structures. So, right, so now we can control the fabrication of alumina, but what is the main intrinsic limitation of this material? Well, it's very good material in terms of the fabrication, and the shapes are very nice, but, it's electronically insulator as well. It has a very big electronic bandgap, so it cannot be used for optoelectronic applications directly, and also it's chemically inert and very stable, which is good for some things, but it's bad for things, especially when you want to develop sensors. So what do people do with this material? Well, so they have developed throughout the years, a lot of range of, or an array of soft and hard modification methods by which, you can condition this material for different applications. First, and for sensing and iontronics, so we can deposit different functional molecules and photo switches to capture selectively the molecules that we want to target, or to enable selective flow of ions through the pores. They're also in photonics and plasmonics. We can deposit light-emitting materials like organic fluorophores or semiconductors for lasing or photoluminescence, also metals for plasmonics, and hybrid systems as well. And then for green energy generation and remediation, environmental remediation, so then we can use semiconductors, carbon-based materials to enable photon to electron conversions and drive these reactions, which actually with the material itself we cannot do, right? And the main advantage of the material is that we can shape these functional materials and give them properties that otherwise they couldn't achieve by structural engineering. So now I'm going to introduce you a few of the applications of the things that we do in our lab. I will start with this work It's nothing. It's again, we don't do top science, nature and science, so don't expect anything outstanding. But it's very good example of what you can do with this very simple material and a very simple surface chemistry. In this case, we are using an interferometer. So what we did is we use a basic surface chemistry, and then we mobilize different blood proteins, right? So basically, we have the chip with blood proteins on the surface, and then we expose this chip to different metal ions. In this case, we use gold and mercury ions, and we study how those how the blood proteins interact with these ions in a controlled environment through optical signals. In this case, it's interferometer, and we measure shifts in the effective optical thickness of the photonic crystal, but actually it's just working as a Fabry Perot interferometer. And then from there, we can monitor in real time the different processes that are happening inside the pores. Up to here, up to 2, this is just, we are just building up the surface chemistry. And then after here is the exposure of the blood proteins to the ions. And you can see this very characteristic pattern shape, which is a bit weird for the standard. So we did further investigation about why this weird shape, right? So this shape comes from conformational changes in the molecules, in the blood proteins when they bind ions. So basically, they change the shape and they expose more binding sites. And those binding sites can be monitored in real time with our system. So it's not actually super sensitive, and that's not the point of it. The point of it is that we can actually monitor these structural changes with our chips, and that gives a lot of information that you know, you need to use very sophisticated techniques for that. And from there, so we can calculate different sensing parameters like the kinetics as well, and also the sensitivity of the system, which again wasn't the objective of this study, but you know, it was very interesting, and that's why I bring it. I'm bringing it for example. Then we can also use, well, more recently we have been using these photonic crystal structures for lasing. So again, we have a photonic crystal structure. So we have this this is the transmission, and we have a very sharp photonic stop band. So that sharp photonic stop band, what it means is that the structure actually is not allowing the light flow through the structure itself, right? It's tuning, in this case, is filtering green light from the band. So if we make a magnified view of the photonic stop band, so there are different type of regions that are very interesting from a lasing standpoint. So let's start with the first one. The top part, as you can see, the transmission is very high. So this is what it means. This what it means is that the light is allowed to flow through the material relatively, right? But it's pretty much like a glasses light, a bit less, right? So then at the bottom of the photonic stop band, which is the transmission is very low. So this is why we say the light is forbidden. So light is not allowed to pass through the material along the pores, right? And then there is these two sections which are called the blue edge and the red edge of the photonic stop band, in which the light is actually slow. What happens is that light is not allowed 100% and it's not forbidden 100%. So it spends more time inside the material. All right, that time is relative, right? We are talking about below milliseconds, right? But it's still enough to get an enhancement emission of the light, which I'm going to try to show. In this case, again, so we start with a bare porous anodic alumina photonic crystal, which is not functional, is useless for lasing. So what we do is we encapsulate rhodamine B molecules, which is a fluorophore and is photoluminescent. And then we encapsulate them in micelles by a process with SDS, which is a surfactant. And then because of negatively and positively charged, so then we can put these micelles on the surface of alumina and then decorate it with a dye. And you want the molecules of the dye be separated to avoid quenching as well. It means that you need to excite the system with less power to get the lasing. Otherwise, what will happen is you need to pump too much energy, and then you will end up burning the fluorophore molecules because they are organics. And this is just the successful functionalization with a photo of the alumina. And this is what we get, right? So After functionalization, you can see that the alumina becomes like pinkish, and you can see that there is a big change in the shape of the photonic stop band. It becomes broader, right? So this is because there are dye molecules immobilized inside the surface, and these dye molecules, sorry, absorb around this region. That's why it makes the band broader. So when we went to the laser, and then we pump our sample with 532 pulse excitation, so when we get a very sharp peak above the photoluminescence characteristic of the dye molecules. So and the position of this lasing it's aligned with the red edge of the photonic stop band, and this is what we call a slow photon laser. So because light spends more time inside the material, so then more molecules of organic are excited at that region of the spectrum, and that's why you get that burst of energy there. So in this study, specifically what we did is to optimize the ratio between the surfactant and the fluorophore. To do that, there are different optical parameters that you need to optimize. One is what we call the gain, which is basically the ratio between the lasing emission and the spontaneous emission, which is the spontaneous emission, which is the photoluminescence of the dye, and then the quality, which is how broad is the band, right? So in this case, to develop the laser, we came up with this compromise, is that we want laser bands that are very, very narrow, or as narrow as possible, but also very sharp, very high intensity, right? So in the parameter to optimize is the product between the quality and the gain, and we found that this correlation between the surfactant and dye is the best. So basically, you want to keep dye molecules separated, but you need a minimum of dye molecules to excite the material. Then after that, what we did is basically some demonstration of why this is a laser. Well, there is a very sharp narrowing of the lasing band up to some input power, and there is a relationship as well between the input power and the output power. Then also to demonstrate that was a slow photon, so then we change the angle, so then you can see that the emission changes the position with the angle, which means that is correlated with the photonic, where the photonic stop band is, because the photonic stop band changes the position with the angle as well, and the depolarization as well. So if the light is polarized or non-polarized, so the polarization is parallel in this case with the excitation laser. Then we have been also doing a lot of work in photocatalysis, using as well a phenomenon that is called slow photons, but also light confinement with optical microcavities. In this case, we fabricate optical microcavities. Won't give much details about what these photonic crystal structures are, but pretty much what you do is you confine light. Sorry. You confine light within the structure by constructive recirculation of light, because you have one mirror at the top and one mirror at the bottom, and you have the cavity. So between these two structures, light of a specific wavelength is confined within the structure. And then what we did, again, alumina is an inert material, useless for photocatalysis. So then what we did is we coated with titanium dioxide by salt gel. We have been using as well atomic layer deposition with our collaborators in Germany, and it works pretty well. So and with that, what we do is we use this structured semiconductor material to photodegrade dyes in this case. So you can see here in one, this is methylene blue, which changes the color in 1 hour, is completely degraded. And we can study as well the kinetics, so at different wavelengths of the light confinement as well, and study which is the most optical arrangement between the position of the light confinement, the absorption of the dye, and with there you can see enhancements associated with the slow photons, but also it's a more tricky system than we thought at the beginning. So it's not only about the slow photons, it also matters about the thickness of the material. So it's more like a compromise as well. It's not always 100% the best alignment with the red edge of the dye works in the, it's the best performing. And we did, as I say, we did quite a lot of work. Yeah, especially CVG did all her PhD on this. More recently, what we have been doing is what we call iontronics. So again, what we do is basically we harness our expertise on this material and we can change the shape and the geometry. So this work was inspired by Bully's work as well. So he recently formalized actually how ions flow through the barrier oxide layer of alumina, and inspired by that, we say, all right, so let's try why we cannot engineer the structure of the barrier layer and see how are the iontronic properties of this material with the features of the barrier layer. And then after that, so well, what is actually ionic rectification? Well, so what happens if you focus on this graph here? So when you are in negative bias, you can see that the current is very high, negative, but very high, right? So it means that the ions actually are allowed to flow through the barrier layer. But when you go, subject the system into a positive bias, so then the current is very small, right? As compared to the previous one, right? So what means is that there is a lot of resistance, and the ions are not allowed to flow through the barrier layer. So this is a very, very nice property to develop sensors as well, because what happens is any change in the barrier layer or the surface of the barrier layer is going to be translated in a shift in the rectification or the current, how the ions flow through the barrier layer, and that's what we did. So basically, we use a very basic chemistry, and then we expose to gold ions, which is pretty standard, and we develop a sensor, based on the different types of barrier layers. And with this, we study the sensing parameters, right? And we found that these sensors are extremely sensitive. They went to the pico level range, so picomolar, range, right? So they can detect they work, in fact, much better at low concentrations than high concentrations. The sensitivity in high concentrations is not great. It can detect high concentrations, but the sensitivity is not great. But at low concentrations, it's extremely sensitive. And that's what we are doing. Many more things in this space in iontronics, but everything is under preparation, and it's the PhD students doing a lot of work in this space, and I feel very, very happy with that. So finally, I think hopefully I didn't take more time than I needed, but I want to thank all my team members, because they are the ones who lift the heavy weight, my collaborators as well, and funding agencies, and of course my friends. So these are my team at the moment, which are the very best, and I feel very proud of these young guys, and also my collaborators, especially Tushar as well, who is coming now. It's been it's not only a collaborator, it's a friend, like most of my collaborators, of course. And thank you very much for the opportunity.
Thank you, Abel, for your very interesting talk. There is time for question now. Is there any question? No. If not, I will go first, maybe with one question. I was wondering if in your work related to the absorption of molecules inside your porous structures, you have also tested the capability to release the molecules, or if this absorption is irreversible.
Yeah, we did. In fact, yeah, we worked for some time in drug delivery back in the times. I moved from that field because, well, I'm not expert in bio. Tushar is way better on that, so he does much nicer works. And you also need good collaborators for that. So with time, like you lose the collaborators and you start moving outside that field. But yeah, we have done a lot as well. For instance, in sensing, what we did is we fill the pores with gelatin, and we study how enzymes degrade that. So it's like the reverse process of the immobilizing molecules. So just remove molecules, and you can track that as well in the system that we use.
Thank you. We have two questions. So the first is Tushar.
Hi, Abel. Great talk as always. Quick question. So you said you were using PVD to deposit, things inside pores. What's the pore diameter you're getting? Do you get any shadowing effect? What's the thickness of the layers that you get?
Yeah, well, it depends on the process, right? So we haven't studied exactly, what's the penetration distance, right? So how deep you can go and how thick. Usually these structures, the photonic crystals are not very, very thick. You know, they are 10 microns or so. So even though they are pores of 5 or 10 nanometers, you can penetrate quite well in vacuum, you know, and you know, doing physical big pore deposition. With LD, we did the work with Robert in Germany, and we didn't check exactly the penetration distance, but you know, my guess is there's some limitation. But in this case, we work with 10 microns max. So
do you
it's
see
not.
any pore blockage happening during the process, or pores are still open?
Yeah, they are still open. Yeah, they definitely. You see how the pores from the top they shrink, they reduce size. Absolutely. But they still, you can still see them in SEM, so it's not fully blocked. Yeah, of that we are sure. What we don't know is, you know, how homogeneous is the layer that we deposit in depth. But you know, because it works for sensing, so we say, all right. So you know, there's a huge difference as well. If the pores were blocked and you only have sensing on the top surface, you can see that in the sensing results. It won't be as sensitive as this when it's inside the pores. It is sensitive as well, but it's not as sensitive as inside the pores. Yep.
Thanks for that.
Thank you. I think we have time for a short question. Luis?
Okay, thank you, Leonora. And Abel, thank you very much for your great presentation and great results as well. I have a curiosity about the last part of your presentation, about this, about the sensing process, about the ionics. So the process seems to be controlled by the barrier layer of the alumina, right? So, but what about the solution? So the solution, it's depend on the result, depend on the solution. You can change. You can find a lot of different solutions, ionic solution. So it's possible to improve or modify, or it's highly dependent about the solution as well. Or I don't know. This is just curiosity. I don't know if this.
Yeah, no, absolutely, 100%. I mean, the rectification signal depends on the barrier layer, the characteristics of the barrier layer, but also in the solution as well, and the pH as well. So yeah, you have to condition the solution to do the sensing if you want to compare, right? So in this case, we compare the effect of the barrier layer, so everything is done in the same conditions regarding the electrolytes. Otherwise, yeah. So, you know, you need to control the pH, you need to control the concentration. In this case, we were using KCl as the ionic conductor, and then we just add the gold ions into one of the sides of the cell. So, and with that, you just change the membrane, and then you study how the barrier layer actually affects the sensitivity and the sensing features.
Thank you very much.
Yeah. Thanks.
Thank you. I think we don't have time for further question, but I would like to thank Abel again for his interesting talk, and I will leave the word to Frédéric. Thank you.
Thank you very much, Eleonore. Thanks a lot, Abel, for the great talk. It is my pleasure now to introduce our second speaker today, who's Tushar Kumeria, and who's from Australia as well. I take this opportunity, by the way, to thank both our speakers today for staying up late at night to give the talk. Because what time is it, Tushar, right now? It's 10 p.m., right? Or 10:30? Yeah.
It's almost,
so thanks.
Almost 10.
Yeah, okay, great. Thanks a lot, by the way. That's great.
I'm at home. Abel is still in office.
Yeah, I haven't realized until you mentioned a couple of days ago asking for the link that you would stay that late at night. So we could have removed maybe the webinar. Yeah, so Tushar is a senior lecturer at the School of Material Sciences and Engineering at UNSW in Sydney. And it has an impressive track record as well, with about 100 peer-review publications in the field of nanomaterials and biomaterials. Is of course very successful in international research, highly competitive international research grants, and has received over 15 prizes and awards from your bio. This information I have. But Tushar is in particular very active in the field of porous silicon-based material for drug delivery and bioimaging, which is the topic of his talk today. So please, Tushar, we are happy to listen to you.
Thank you, Freddie. Yeah, thanks everyone for giving me this, like staying here, and thanks to Netpore for giving this opportunity to me. As Freddie said, we work a lot on porous silicon-based materials, but we work on other type of materials as well. I'll start with giving a background of what my journey has been. I am originally from India, but I did my PhD at Uni Adelaide. And Abel was one of my supervisors, and we had the best time. Here's a photograph of us from that time, from 2013, 2012. Abel is here, and this is me. After that, I moved to UC San Diego, and some of you will recognize this person here. I did my postdoc with Mike Saylor. Mike is here. So this is during the summer school that we have our kayaking tour. So we were going for this kayak tour, and that's what this photograph is from. So I moved to UC San Diego in 2015, and in 2017 I moved back to Australia. I got a fellowship to come back to Australia. So I moved back to University of Queensland in Brisbane, which is about 900 kilometers up north from where I am right now. And then I moved back to Sydney in the middle of this pandemic, 2020, around middle of around June, July time. So we've only been working in the lab for about a year at Sydney. We've been in lockdown for quite a long time. So I'll show you some data of what we've done at Sydney, but a lot of this data is from all over the places where I've worked in the past few years. So let's get started into what we do in the group. We make porous silicon-based materials. In past, I worked on porous alumina-based materials. As Abel said, we started doing photonic crystals, porous alumina-based photonic crystals for sensing application. We did work on titanium nanotubes. We still do some work in collaboration with Abel and others on these two materials, but most of the focus of the group right now is porous silicon, mesoporous silica, and composite nanofibers. And today I'll mainly talk about these two materials, porous silicon and mesoporous silica. So I'll give you a background of what, how these materials are made. Porous alumina, porous silicon, and porous titanium or titanium nanotubes, as we say, are made using electrochemical anodization. As the name suggests, you have a power supply through which you supply current in presence of an electrolyte, and your substrate acts as a positive electrode. So you have a negative electrode, and that process ends up drilling holes into the substrate. So that's the case with porous silicon. Whereas in case of aluminum and titanium, you end up forming an oxide layer, which is porous. So that's what, we work on. Some of you I know work on porous silicon. I know Freddie has worked on porous silicon. Luca Baurino is here. I've met some of you at PSST in 2016, I remember. So I know some of you work on porous silicon and are familiar with it. But this is a video from Mike's lab, so easy to explain how it's made. So this is how we start. We pack a silicon wafer in an etch cell. And after packing the silicon wafer, we apply current onto the silicon wafer in presence of an electrolyte. And we can either keep the film on top, the porous film that is formed on top of the silicon wafer, or we can lift it off to form freestanding film, which we can divide to form micron or nano-sized particles, depending on what the applications are. Right, so these are porous silicon particles, which are micron in size, and we can tune the pore size depending on how we etch the silicon wafer. Let's look at why we use porous silicon for various different applications, why that we do. The main reason is we can tune the pore structure. We can have pores ranging from less than 10 nanometers to hundreds of nanometers, depending on how you etch them. So that's a very good controllability that allows you to either incorporate molecules inside the pores, or if you are working on sensing, to attach antibodies and probes inside the pores so you can pick up things at very high sensitivity. Surface chemistry is highly tunable because you have a surface oxide layer, and very well established silane chemistries can be used to form surface layers of various different types. You can have them hydrophilic, hydrophobic, positively charged, negatively charged, and there's been many other techniques to functionalize porous silicon for specific applications, depending on the need. We have done a lot of testing of porous silicon with various different type of cell lines. I'll show some examples of those, but others have done those as well. We know that being, porous silicon being porous, there's a very large open pore volume. So we can utilize that to incorporate payload molecules, especially for drug delivery. So we get really high drug loading capacity. We can tune the release profiles depending on the particle size, depending on the surface chemistry. And we know that porous silicon is biodegradable. It dissolves out as silicic acid, right? And the other fantastic property of porous silicon is that it's photoluminescent. Depending on how you make it, you can have particles that you don't need to tag them with any fluorophore, and they fluoresce by themselves. So you can activate the fluorescence, photoluminescence of porous silicon. What we use porous silicon for is a range of different things. So first example, as we use them for drug delivery, we've utilized them for oral delivery, systemic and local delivery. We've packed a range of different molecules into it. We've packed proteins, small molecules, and even RNA. Nowadays, we're working on RNA delivery using porous silicon-based materials. We use them for tissue engineering application. We do bioimaging, a lot of it nowadays, by designing porous silicon in specific manners. I'll give you one example of it at the end. And we utilize this for a lot of sensing application, mainly chemical and biosensing application. Abel and I have a couple of successful funding applications on biosensing using porous silicon and their composites. I won't talk about sensing today. I'll mainly focus on drug delivery and bioimaging, but this is all the capabilities that we have and that we conduct in the group. So to start with the example, as I said, we've only been working at UNSW for about a year. We've been in lockdown, but we've done some interesting work. So this is a work from when I was in Mike's lab. We made porous silicon-based photoluminescent particles, which were loaded with a protein. And the idea was to create self-reporting ophthalmic formulation. So these were targeted for treatment of age-related macular degeneration. Mike has been working on these for quite some time. Initially, the idea was to utilize the photonic properties of these porous silicon particles, but it's very difficult to pick up the photonic signatures in the eye, whereas photoluminescence, you can pick it up very easily using commercially available systems. So what we did was we designed porous silicon particles, and based on how they were treated thermally, you could have different photoluminescence quantum yield, and we picked up the particles with highest photoluminescence quantum yield and looked at their degradation. So as these particles degrade, you see a decrease in their photoluminescence. And this decrease can be correlated to the release of payloads from inside the pore. So if you fill the pores with with a payload, in this case, this was a BSA molecule, which was tagged with FITC. So as FITC labeled BSA comes out, the photoluminescence goes down. So you could, in real time monitor how much payload remains inside the pores. And depending on how thick the oxide shell is, when I say how thick the oxide shell is, it depends on how long these particles have been heated for. So this is thin shell, this is medium thick shell, and this is the thickest shell at 45 minutes of heating at 700 degrees Celsius, right? So the thin shell particles, they act as a real-time indicator, whereas the thick and medium shell particles, they act as an end-of-life indicator. So what tends to happen is you don't see any decay in photoluminescence till the time about 80% of the payload is released out. So that's a very good indicator and useful for doctors because that you don't actually need real-time indication. You just need to see an indication that the amount of drug has gone below a threshold and it's the time to do another dose. Because right now, The problem is these patients for age-related macular degeneration, they need to go to clinic, get an injection jabbed in their eye every 3 to 6 weeks, depending on their age and their metabolic rate. And doctors rely on reoccurrence of the symptoms to decide when to do the next dose. So if they could, visually monitor or objectively monitor how much dose there is in the eye, they could tune the dosing profile and dosing regimen much better. We also looked at these particles using a very cheap camera, because the idea is to not just use it, these photoluminescence spectrums are taken with very expensive, spectrophotometer. Whereas in clinic and in the field, you want the system to be applicable at the lowest cost possible. So this is a very cheap camera, and the idea was, can we pick up the photoluminescence of these particles? And this is a 96 well plate full of particles and 0.1 molar KOH, and we can see that these particles, we can pick up the fluorescence, and as they degrade, the fluorescence integrated intensity goes down. So we can see it using even the very cheap cameras as well. So they can be deployed in the field very easily. We injected these particles into rabbit eye, and this is what you see here. This is a rabbit eye with porous silicon particles injected into it. They tend to form a bolus. And this is a color image, whereas this red image that you see here is the photoluminescence image. The limitation of the system that we had was the field of view of photoluminescent camera was very small. So we had to take multiple images together to stitch multiple frames together to get the integrated intensity. So that's something that is still going on. We did load a small molecule payload. We didn't want to inject, a protein payload to start with. So we worked with triamcinolone acetonide. We again did in vitro photoluminescence decay and drug release. And we can see there's a correlation between the two, which is almost zero order. In vitro photoluminescence decay and in vivo photoluminescence decay matches quite well as well. For up to 10 days, what we see quite a well-tracked photoluminescence decay. So we are quite hopeful that these can be utilized for in vivo tracking of formulation amount as well. So that's one work that we've done. More recently, we've ventured into composite systems with porous silicon, and this is an example of porous silicon-based thermal-responsive hydrogel. And the idea was to deliver these hydrogels in the nasal cavity to treat the nasal inflammation. So if you ever have had, congested nose and have taken a nasal puff, you see that, a lot of the formulation goes to back of your throat. You taste it. The reason you taste it is it's based on an aqueous system. You spray it and a lot of it, your nose and your mouth are connected. It can flow back through. The idea was, can we have a formulation which we spray and forms a coating inside the in your nasal cavity as it hits a relatively higher temperature than the storage temperature. So this system is based on Polaxamer 407. We incorporated a highly lipophilic drug, mometasone furoate. So this is the other advantage of using porous silicon. That drug cannot be directly incorporated into this Polaxamer-based hydrogel because it tends to crystallize out and the release profile is quite poor. I'll show you that in a minute. But that's what porous silicon provides an advantage for. So it provides a medium to incorporate the drug, a highly lipophilic drug, and improve its solubility. So when the formulation is at 8 degrees Celsius or a storage temperature, it's liquid. Once you heat it to about 32 degrees Celsius, it becomes a gel. So this temperature is not 37 because the temperature of the nasal cavity is generally lower than your body temperature. That's why it's designed to gel around 32. It's actually designed to gel around 28, 27 degrees Celsius. And this is what you see here. So these are rheograms of these hydrogel. The pure hydrogel gels at around 27 degrees Celsius, whereas a gel which has about 13 milligram of these porous silicon particles per gram of gel has a gelation temperature of 28 degrees Celsius. What you see here is 0.18%, 2 and 5 is the equivalent drug amount. So this is the maximum drug amount, 0.58%. There's a commercial formulation of mometasone furoate in the market at 0.1 weight percent. We wanted to see what happens if we increase the amount of drug, equivalent amount of drug, beyond what's available in the market. So what we see is when you have this composite hydrogel, you see a much better drug release or much higher amount of drug being released out compared to when the drug is directly added into this hydrogel itself. So when there's porous silicon, we see more drug come out versus when the drug is directly added into the hydrogel. And it's the case with all three formulations, 0.1 weight percent equivalent, 0.2 and 0.5 here. The reason, again, as we've done some XRD study, and we believe the reason is that the drug remains as an amorphous form. So it's more soluble and more of the drug can come out versus when the drug is directly added into hydrogel, it crystallizes out and does not dissolve as fast. The other thing we did was we did drug deposition in human nasal tissue. So we got human nasal tissue from a hospital that we work with, and we looked at drug deposition. So drug deposition from the formulation that just had the hydrogel and the drug incorporated into it, very little amount of drug got in, deposited into tissue because drug was not soluble. Whereas the composite formulation with porous silicon, we see 19 times more drug being deposited onto the tissue, human tissue, per gram compared to just the drug itself. We looked at the toxicity of these formulation, and what we see is we see only the positive control, which is zinc sulfate. That's the only molecule which came out to be toxic in LDH assay, and so is the case in histology as well. So in LDH assay, none of our formulation nor the vehicle, which is just the plain gel, they showed any toxicity. And these are histology images showing the same thing here. So this is the positive control. So you see, damaged basal cell layer, olfactory epithelium lining is damaged as well, whereas all the other things, other formulations, you see none of that. You see basal layer is intact and olfactory epithelium is intact as well. So this is one example of what we've done very recently. The other thing that we've been trying is to incorporate small molecule drugs for antibiotic application or antibacterial application. And in this case, this is a specific drug which has an inverse problem. It's very highly soluble, but if you take this drug orally or if you take this drug via an IV injection, the PGP efflux pump on the cell, they efflux it out into urine and most of it is cleared out very, very quickly. And the second problem is that this drug degrades really, really quick. So the idea was, can we create a system based on functional molecules on the porous silicon particles which prevent the PGP efflux of this drug out from the cells. So we looked at a few different surface functionality. Here is just PEG with amine group at the top, and this is tocopherol-based PEG, which is vitamin E, right? So that's what you see. So these are the two particles that we tried. We tried one which is the controlled porous silicon as is, one with tocopherol, which is vitamin E, and PEG with amine terminal group. And what we see here is this is the important table to look at. So efflux ratio of the drug itself is 2.6. And when I say efflux ratio, how we measure this is we have a Kakutu monolayer cell model. So we look at absorptive permeation and secretive permeation. So in absorptive permeation, we put our particles here and look at how much drug got deposited or got collected in the basolateral chamber. And in secretive permeation, we put the particles here and look at how much drug got secreted into the apical chamber. So we take a ratio of how much drug goes from either end in two assays, and this is what determines the efflux ratio. So what this shows is efflux ratio of meropenem by itself is very, very high, which means when we put the drug here, more of the drug goes out in secretive pathway versus when the drug is loaded into particles, especially tocopherol based. So more of the drug gets retained in the basal chamber. So inside the systemic or, in vitro, if we call it in the in vitro sense, inside the systemic circulation. So it does not get effluxed out. These are just the efflux cumulative transported amount. I won't go into details. The other thing we wanted to look at was to, as I said, the drug degrades really quickly. So half-life of this drug, even at room temperature, is very, very short. Within few hours, about 30 to 40% of the drug degrades out. And patients are required to take intermittent doses. So how this drug is given, patient goes into clinic and they get an IV line for 1 hour, then the drug gets stored back in the fridge, cooled down, and applied again. So the idea was, does this drug retain stable when we load it into the particles? So we developed a system, a co-culture system, where we had Kakutu monolayer in the apical chamber of this transwell culture and bacteria in the basolateral chamber. So what we see is, we see a decrease in bacterial population, which means our drug inside the particles was still active. So it did function as it was supposed to. So that's one example of what we've done with porous silicon. I'll quickly jump into porous silicon, mesoporous silica-based system. We do a lot of this now in the lab. We make a range of different type of mesoporous silica. These are solids. These are MCM41 type. Have very tiny 2 to 3 nanometer pores. These are rod stripe, same type of particles which have 2 to 3 nanometer pores, and these are dendritic. They have quite a large pore opening, can be up to 10 to 14 nanometers. So we make a range of different type of mesoporous silica nanoparticles in the lab. Like in the previous study, I showed you that we incorporated meropenem drug into porous silicon and different functionalities. The problem with that formulation was the drug released out really, really quickly because the drug is highly, highly water soluble. So we wanted to look at, can we encapsulate it into a system which prevents or controls the rate of release of the drug? So we worked with a microfluidic based system to create microparticles where the drug was loaded into mesoporous silica particles using a liquid CO2 method. We had one set up. Now we've got a bunch of more high pressure syringe pumps in the lab. So we're setting up more liquid CO2 and supercritical CO2 facility in the lab. So in this case, liquid CO2 was used to incorporate the drug and these into mesoporous silica particle, and then these were coated with Udragid-based polymers. So Udragid-based polymers are FDA approved, already used for oral delivery, commercially available, and that was the reason to make this type of system. We tried 3 different types of Udragid system. One is RSPO, RS100, and S100. So these 2 are timed release system, whereas this is pH sensitive. So this starts to release above pH 6.5. So that's what you see here. For S100 system, you see a pH dependent release. You don't see anything releasing at pH 1.2. Once you switch the pH, you start to see the amount of drug come out quite rapidly. Whereas in this case, both of the system release even at pH 1.2 and pH 6.8. Again, we looked at the absorptive and secretive transport, and what we found was that the meropenem by itself is quite high. So more of the drug when put in here shows up here, which should not be the case, right? Whereas when this drug is incorporated into particles, especially RSPO, more of the drug retains inside the basolateral chamber, so showing that efflux pumps are suppressed and more of the drug remains inside the systemic circulation. So we're taking this into in vivo now. We'll see how things go. We'll be running some pharmacokinetic studies now. We'll have the data in a few months, fingers crossed, it'll go well. We also, as I said, we do photoacoustic imaging as well in the group and other type of imaging. And one of the simplest way that we've done photoacoustic imaging was that we took porous silicon, mesoporous silica, converted into porous silicon using magnesiothermic reduction and functionalized it with antibodies for specific targeting. And what photoacoustic imaging, I don't know if any of you know or some of you know, in ultrasound, you shine ultrasound waves, you pick up the reflected ultrasound waves. Whereas in photoacoustic, you shine pulse laser to excite thermoacoustic vibrations, which are in ultrasound region, which get picked up by the ultrasound transducer. So this is what photoacoustic imaging is. This is the porous silicon particles functionalized with the antibody after PEG and the DLS curve, and you can see the size change is not much. The particles still retain their size, and it does not go above. The starting size was about 60 nanometers, and the particles after functionalization went to about 70, 75, which is not bad for what we actually wanted to do. Initially, we scanned the whole spectral range for photoacoustic imaging, and we found that the particles show a peak photoacoustic response at about 700 nanometer excitation. And this is what we use for all the further studies. The reason to do this is there's a commercially available and clinically used dye, indocyanine in green. The problem is the dye, loses its signal quite rapidly. Whereas the particles, they retain their signal over a very long time of excitation. So some of these scans can take the photoacoustic intensity. This is ICG in 2D, in 3D view inside a tube, and this is porous silicon. And compared to ICG, we get about 6 times better photoacoustic signal at the same concentration. This is a mouse flank, right flank. So subcutaneously, injected PBS, we see nothing as expected. Silica particles don't show anything because they don't absorb in the IR range, whereas porous silicon absorbs a bit more in around this range. I wouldn't, silicon is transparent to IR, but it absorbs quite heavily around 600-700 nanometers in the spectral range. And that is what we see here as well. So when these particles are injected subcutaneously, we see very strong photoacoustic signal. 2D render, 3D render, this is again an ex vivo. I wouldn't go into details. We looked at their uptake into cells with particles functionalized with this antibody. This specifically targets ovarian cancer. We did in vivo studies as well. So this is pre-injection. This is the tumor volume. This is 10D7 targeted particles. And these are control particles which are non-tagged with 10D7. And what we see is at 48 hours time point, there's a significant difference in terms of accumulation of particles. And what this shows as well is that these particles are capable of allowing for in vivo bioimaging as well. I am currently funded by NHMRC, or I recently got off of an NHMRC fellowship, and the main focus of that fellowship is to deliver protein payloads orally into inflammatory bowel disease. And one of the aims in the study was to look at what happens when we orally give porous particles. So if we give mesoporous silica particles by themselves, so this was the idea, we would need to functionalize this, and we know if you functionalize the surface, the accumulation can change. So we wanted to look at what happens to pristine particles, but you can't do this with mesoporous silica. This is where porous silicon shines because it has inherent photoacoustic activity. So a small molecule dye 4 hours after oral gavage gets cleared out from this is GI tract of a mouse. So 4 hours after, it gets cleared out within 4 hours, whereas porous silicon particles after 4 hours, they still are there. So it shows clearly that, giving a particle-based formulation makes sense because they get retained in the GI tract for longer. And this is basically the intensity. I can stop here, just will show, the intensity difference compared to ICG is 3 times more. We have done more work with photoacoustic imaging. I won't go into details. I think I'm over my time. But in terms of people who've done a lot of stuff, these are the people who've actually done a lot of stuff. This is my group at the moment at UNSW. There's a lot of collaborator. Abel is, has been a friend and a collaborator for a very long time, and we've been working on a bunch of things, and hopefully you've learned something today, and we form new collaborations through this. And I would like to thank these funding agencies who have funded this work. These are some recent photographs of me and Abel. We met in November as well, but we forgot to take photograph. We were too busy drinking beers. And thank you, everyone. Thanks for listening.
Thanks a lot, Tushar, for this great presentation, very informative and such a great work and interesting applications that you have presented. So we have a time for questions.
Yes, I have one question, if I may.
Yeah, sure.
Thank you, first of all, great presentation. You mentioned with your done a lot of tests with toxicity and biodegradability of the silicon. I was just wondering if you've, so I get questions a lot too about how does the actual dopant of the silicon have an influence on the material, whether you're using, P-type or N-type. And then also, of course, you can get highly doped with arsenic, and then people say, you definitely don't want that in the body. So I was just wondering if you have any insights on the dopants or if they make a difference at all.
They definitely do. We mainly work with highly P-type porous silicon, so highly boron doped. Very rarely with N-type. Most of the stuff that I've shown you is with highly P-type porous silicon. Their degradation rate we mainly control based on the size of particles and the surface oxide layer. But we've not looked at, dopant density. That's something to look at. Yeah, that's quite an interesting question, but yeah, I can't answer. We've not looked into it.
Okay, but you didn't see any kind of, let's say, negative influence because of boron due to, let's say, I don't know.
The thing is, we don't have anything to compare. We've always worked with P-type boron doped silicon, and that's what we base everything on. I can certainly tell you that the mesoporous silica based samples, they degrade relatively slower compared to the porous silicon based samples which are doped. So we've done that comparison. That's what we have. But in terms of porous silicon made from electrochemical etching, we've always used the P-type doped, highly P-type doped.
Okay, thank you very much.
Thank
Great
you.
talk.
Thank you.
Luis, have a question?
Yes, thank you, Frederick. Thank you, Tushar, for this nice presentation and amazing results as well. I have a curiosity about the last part of the photoacoustic imaging. What is the size of these particles, and if you need to do some special treatments for this specific application?
So the particle size is about 70 to 80 nanometers. So this is here. The conversion that we have done using the process, I am saying it's magnesiothermic, but I can't reveal the whole process. It's the IP thing. But it's a very controlled process. We have controlled the process in a certain manner to retain the structure. And I know some people have tried, but retaining the structure after conversion is quite difficult. So we've been working on this quite a lot. We've figured out a way to retain the structure and the size of particles without destroying. We see the particle. So if you look at this study here, so this is mesoporous silica. You see these particles are similar to the ones that I'm showing. These are quite, they're not as rough edged. Whereas after reduction, the other particle became quite rough. So they've lost some of the mass off of their surface. That is quite evident.
Okay. Thank you very much, Tushar. Pleasure.
Thank you.
I have a quick question for you, Tushar, as well. I'm going back to the beginning of your talk on the eye application. In the rabbit, you showed the photoluminescence decay in vivo and in vitro of your system in few hours or in few days, sorry. I remember for this project that they were requesting some long-term sustain and stability of the compound. And I was wondering if you have any treatment, because it's stable about 10 days, right? Then
so the problem here is, so we actually we took out the eyes and the particles were there up to 18 weeks. I think our system, the eye imaging system, was not very accurate because we are taking 2D stacks while these things form a bolus of a 3D stack. We pick up one layer, and what we this was a very fun project. So we needed 4 people to do one experiment. One person would hold the rabbit, other person, despite being anesthesia, hold their head. Other person will pull their eye to another corner. One person will hold the machine and the other person will trigger the camera. So this was quite challenging to take the whole sequence and club it together. The data is based on the best images that we have taken and clubbed them together. But I think this could be improved. The particles remain there for 18 weeks. They were in the eye. We've seen it, but it's just we couldn't pick it up with photoluminescence camera, and that's why you see the
All right, and I have another very quick question going back to this magnesiothermic reduction of the porous silica. You said that it's a very well controlled system, and I know it's pretty difficult to maintain the structure. Did you convert all the silica into silicon in your system? Were you able to evaluate?
I think we have very high efficiency. I won't claim all of it got converted, but I think the efficiency is quite high. I don't know if you have a technique how to quantify that would be good. We've not been able to figure out how to quantify how much got converted. We mainly basing it on the optical analysis that we do and the XRD that we've done. We've done XRD and we don't see any lowering at XRD, we don't see any silicon dioxide peaks, or if they are, they become very, very low. That's what we are basing our analysis on, that most of it got converted.
Yeah, and it seems that you maintain the structure very well. So you get, okay. Thanks a lot, Tushar. I think it is time to thank our 2 speakers, and I wish you a great day or a great night, evening and night for the Australian guys. Thank you very much for attending the webinar today. Bye-bye.
Thanks, everyone. Thanks for the chance. It has been lovely.
Thank you again. It was great.
Bye, everyone. See ya.
Bye. See you.
Bye-bye.